Welcome back to the deep dive. So you sent us this really wonderfully detailed piece of horticultural writing.
Right, your Notes on Gardening, part 748.
Yeah, and we're tearing into this discovery about Coleus propagation. But it's really, I think, a shortcut to understanding some fundamental plant biology.
That's a great way to put it. I mean, if you want a fast, clean, really effective way to root Coleus cuttings, this source gives you a clear path.
So our mission today is to synthesize that,
Yeah.
to figure out the science behind it.
Exactly. We're looking for maximum efficiency in root development. And, the technique here, it kind of challenges that common wisdom of just sticking a cutting in a full jar of water.
It really does.
Yeah.
And the whole narrative pivots on that initial observation. We all know the classic method, right? Fill a jar, stick the cutting in, and wait. But the author of these notes, they tried something almost minimalist. They found that the water level, keeping it intentionally low, and then placing the plant in a shaded area, that was the critical start.
It's almost like a purposeful deprivation. The whole setup is designed to keep the bulk of the stem, especially that main node where roots pop out, completely above the liquid.
Okay, so let's get into that precise setup, because it sounds like the details are what make it work.
They are.
The notes really emphasize that the water level has to be minimal, just enough to wet the very bottom of the stem.
Right, just that little contact point. It's all about maintaining what the source calls turgor pressure.
Without that tiny bit of moisture, the whole cutting just wilts, and I guess the experiment is over before it even starts.
Immediately. You're basically giving the plant just enough water to keep its cells rigid, to keep the leaves firm and the stem upright.
But you're actively denying the rooting nodes easy access to all that water.
It's a physiological tightrope walk. You probably have to check it daily, maybe even hourly if it's warm.
That seems like a lot more work than just topping up a jar once a week. I mean, I have to wonder if all that effort of measuring and monitoring, does it cancel out the benefit? It sounds a bit high maintenance.
That's a fair point about the setup, but the speed of the result is what justifies it. And here's the payoff, the real surprise.
Okay.
Because the stem is hydrated but not submerged, the roots start to sprout from the nodes above the waterline.
So aerial roots.
Exactly. They're seeking moisture, for sure, but they're also exposed to something that water normally limits.
And the data in the notes on this it's pretty staggering. It wasn't just that the roots grew, it was the speed.
A huge difference.
The experiment showed these aerial roots were ready for transplant in about half the time of the submerged ones.
Yeah, the notes specifically said something like viable roots in 7 days for the aerial method versus 14, maybe more, for the standard jar method.
That's incredible.
And what's fascinating is that it's all about placement. The location relative to the water determines the speed. The plant is, in a way, choosing to grow roots in the humid air instead of underwater.
Which forces the big question then, why? Why is the air better than the water for growing roots?
And that brings us to the core biological mechanism, the why behind it all.
Okay, let's unpack this. The notes call it the humidity chamber effect, the HCE.
Right. And the HCE is really just passive environmental engineering. It's quite brilliant.
How does it work?
Well, you put a small amount of water in a contained vessel, like a narrow glass jar. The airspace above that water line, it gets saturated with moisture very quickly.
So because the jar is contained, the water vapor just builds up.
It builds up until the air in that space hits about 100% relative humidity.
So you're not just relying on the humidity in the room, you're trapping it, concentrating it, and I guess the shape of the container, tall and narrow, that helps stabilize that little microclimate.
Precisely. That high humidity stops the cutting from drying out, which is what the water usually does. But, and this is the key, the HCE does something else at the same time.
It gives the rooting nodes access to oxygen.
A massive, almost limitless supply of atmospheric oxygen.
So it solves the two big problems at once. It prevents wilting, and it provides the fuel for cell growth. This isn't just about hydration anymore. It's about respiration.
It is entirely about efficient gas exchange. And that's the crucial insight from the sources here. Root cells, like all our cells, they need oxygen for aerobic respiration.
To get the energy to divide and grow.
Exactly. And in that HCE environment, oxygen is just everywhere in that humid air, so those aerial roots can just hyper-accelerate their development.
That completely changes how I think about traditional propagation.
Yeah.
So if the HCE is all about maximizing oxygen, what's holding back the old school deep water method? Why is it twice as slow?
It's what the notes kind of implicitly identify as the dissolved oxygen bottleneck.
It's a great term for what's basically a physics problem, huh?
It is. Standing water, especially at room temperature, can only hold so much dissolved oxygen. We're talking less than, say, 10 parts per million.
And as soon as the roots start to grow and respire, they use up that finite supply really fast.
And once it's gone, root growth just stalls. The environment becomes hypoxic low in oxygen.
Which is probably why roots sometimes rot in standing water.
Yes, that's a huge part of it. Hypoxic conditions are perfect for anaerobic bacteria and fungi. You get stem rot. The HCE completely avoids that because the stem isn't even submerged.
You know, this connects directly back to that classic advice we always hear. Change the water every 2 or 3 days. I always thought that was just about keeping it clean.
We all did, but in reality, changing the water is just a crude, repetitive way to try and fix that dissolved oxygen bottleneck.
You're dumping out the old oxygen-depleted water and putting in new water that has a fresh, 8 or 10 parts per million of oxygen for a few hours.
It's a totally inefficient system that physics forces on us.
So the HCE is just a brilliant passive hack. It lets you completely sidestep the manual labor and the physical limitation of water itself. You're swapping out dissolved oxygen for the infinite supply of atmospheric oxygen.
And if we connect this to the bigger picture, you're right. It's just a more efficient system of gas exchange for starting roots. It proves that the root's biggest need isn't saturation, it's respiration.
So now that the sources have established oxygen as the true speed governor, it naturally pivots to the future. What if? What if you could give the submerged roots the same amount of oxygen?
Exactly. And that's the follow-up question raised in the notes. It moves from passive observation to active optimization. Can we eliminate the bottleneck with machines?
And this is where the air stone idea comes in. I thought this was just genius.
It's great.
Using a small air stone, like from an aquarium, hooked up to a little pump to constantly oxygenate the water.
You'd essentially turn your propagation jar into a tiny little aerated bioreactor.
Which raises a really important scientific question. Is the HCE successful just because it maximizes oxygen, or is there something special about the roots being in air?
That's the test. By adding an air stone, you could theoretically get 100% dissolved oxygen saturation in the water. Could you match the speed of the aerial roots? Or maybe even beat it?
So you'd have the active method, the air stone, versus the passive HCE method. But there are trade-offs.
Well,
the HCE is silent, it's cheap, no electricity.
Whereas the air stone needs a pump, tubing, maintenance. It makes noise.
For the casual gardener, the low-tech HCE seems like the clear winner. It's just easy and fast.
I agree. But for a serious propagator who needs speed and uniformity, that air stone experiment is crucial. If those submerged, oxygen-rich roots grow as fast or faster, it confirms oxygen is the only thing that matters for speed, not humidity.
And the notes bring up another critical point for the HCE roots: transplantation shock.
Yes, that's a potential downside.
Those aerial roots grew up in a perfect 100% humidity environment. They might be really delicate. When you suddenly plunge them into dense, drier soil, they could struggle even if you harden them off.
And that's where the air stone concept really shines. Roots that develop fully submerged are already tough. They're used to being in a denser medium.
So if you can get HCE level speed with submerged roots, you eliminate the shock risk.
You do. You're not just accepting the limits of water, you're actively managing the one ingredient water limits most: oxygen.
So what does this deep dive mean for you, the person listening? You basically now have a complete two-pronged strategy for rooting Coleus.
That's right.
You can go with the low-tech, passive HCE method, low water, shade, and you get rapid aerial root growth.
Or you can be the true experimentalist. You can try the high-tech, active oxygenation with an air stone and really push the boundaries for submerged cuttings.
And both strategies are now backed up by a solid understanding of root respiration. I think the core takeaway from this whole review of the notes on gardening is just so clear. The speed of root propagation in Coleus, it's so much less about contact with water and so much more about the continuous availability of oxygen.
Right. That air-saturated microclimate from the humidity chamber effect is powerful precisely because it bypasses the physical limits of dissolved oxygen in water.
It's amazing insight.
And it really opens up a huge area for you to explore. I mean, think about it. If continuous high-level oxygenation is the secret for Coleus, how far could we push it for other plants?
Especially the ones that are notoriously difficult to root.
Exactly. What if we could control the entire atmospheric environment? Go beyond just humidity, maybe control the pressure or the specific gas mix around the cuttings. Could we dramatically change propagation speed and viability across all of horticulture? It really makes you think about the broader power of root respiration.